Okay, thanks very much. Very nice to be here. So some of you will have seen me talk last week at the conference, and I'm going to be talking on some of the same material, but I'm going to flesh out a lot more detail in what I said last week in a shorter talk. So hopefully, if you were at the conference, there'll still be something that's new and interesting to you, with luck. If you weren't at the conference last week, then more of the material will be new. And I won't spend a lot of time on an introduction to matroids. I'm sort of hoping that everybody will have at least seen the definition of a matroid before or have some intuition for matroids. I won't spend a lot of time on that, but I will just go through the definition to make sure that everybody's on roughly the same page. And if you have any questions, just let me know. Very happy to receive interruptions. Okay, so as you can see, I've got a long list of co-authors on this project, and that's basically because I've given roughly similar talks quite a few times over the last few years in various places around the world, and every time I've given this talk, I've ended up with a new co-author. I feel like I'm the Pied Piper of Hamelin, with like mathematicians trailing behind me. It's a really seductive and interesting problem, so I hope you find it interesting. Let's start with some introductory matroid material. So like I said, I'm not going to give a lot of motivation for a matroid, but if you know nothing about matroids, here's all you really need to know for this talk. A matroid is just a special type of hypergraph. It's a special type of finite hypergraph. So a matroid consists of a finite ground set, usually labeled by E, along with some collection of subsets of E. And those subsets of E are called the independent subsets of the matroid. There are three straightforward axioms that the independent sets must obey in order for this to be a matroid, and I've put those axioms up on the screen. But I'm not going to motivate them or talk very much about them. My calculation is, if you've seen this definition before, if you're familiar with matroids, then you gain nothing from me talking about it. And if you haven't seen matroids before, you're also not really going to gain very much from me just reading the axioms out. So instead of concentrating on what the axioms say, I will just skip to two important families of matroids. Okay, so here's the first, the family of representable matroids. So in this case, I have a vector space V, and I will say that F is the field of scalars for this vector space, and my ground set E is going to be a finite set of those vectors. That's my ground set. Now I need to define what independence means. So I'll say independence in the matroid is just linear independence in the vector space. Then the independent sets satisfy the matroid axiom, so this is indeed a matroid. And any matroid that arises in this way from vectors, I will say is a representable matroid. If I want to be more specific, I will say that it is representable over the field F, or I will say it is F representable. Next important class of matroids. I start with a graph. My ground set E is the set of edges of the graph. Now I need to define what independence means, and I will just say that a set of edges is independent if it is acyclic. So the subgraph corresponding to that set of edges contains no cycle, in other words, it's a forest. Okay, so the independent sets are exactly the forests. The independent sets now satisfy the three axioms for matroid, so this is indeed a matroid. Any matroid that arises in this way is a graphic matroid. Okay, any questions so far? Okay, so now I'm going to introduce a third family, which will be less familiar to you. If you've read an introductory paper on matroids, then you will have definitely seen these two classes, but you probably will not have seen this next class. Okay, so here we go. Like the case with graphic matroids, I'm going to start with a graph, but I also have a group H. Now, I am going to direct every edge of the graph and I'm going to apply a labeling of group elements to the edges of the graph. So in this example, my group H is S3. That's the permutation group on 3 elements, and I've written the permutations in cyclic notation. Okay? So I've now directed every edge and labeled every edge with a group element. As with the graphic matroids, my ground set is going to be the set of edges, so I need to decide which subsets of edges are independent. And in order to do so, I need to have I need to distinguish certain cycles of the graph. So that's what I'm going to do next. I'm going to distinguish some cycles which I call the balance cycles. And I do that by walking around a cycle and taking the product of the edge labels that I encounter as I go. So I'm walking around this cycle and I encounter the labels 1, 3, 1, 2, identity, and now the inverse of 1, 3, 2. And I take the inverse of 1, 3, 2 because that edge is directed against my direction of travel around the cycle. Okay? So if I make that calculation, the group element that I get is the permutation 1, 3, 2. Now, we can see that that product walking around the cycle is not well defined. It depends upon my starting point and it depends upon my choice of direction around the cycle. So if I choose the same cycle but with a different starting point, I may get a different product. I now get 1, 2, 1, 3, the inverse of 1, 2, the inverse of 1, 3, 1, 3, 2, and the identity. It's a different product. It's 1, 2, 3. But using group theory language, the products that I get will always be conjugates of each other. And that means that if I get as a product the identity, the group identity, then no matter how I start, no matter how I walk around the cycle, I will always get a conjugate of the identity, which means the identity. So any cycle where I get the identity, it will always be the identity no matter how I walk around the cycle. And so that distinguishes those cycles. I will say that those are the balanced cycles. All right? Balanced means I get the group identity when I walk around it taking the product. So now I have enough structure to define a matroid. My ground set is the set of edges. My family of independent subsets are the sets that contain no balance cycle and at most one cycle per connected component. So if I look at this highlighted set of edges, there is no balance cycle. We've already seen that the blue cycle on the left is not balanced. You do not get the identity when you walk around that cycle. We could also verify that when you walk around the right-hand blue cycle, you do not get the identity. So this set of blue edges does not contain a balance cycle, and it contains at most one cycle per connected component. That makes the highlighted set of edges an independent set. It's a little bit harder to see, but this collection of independent sets really does satisfy the independence axiom, so I really do have a matroid here. And any matroid that arises in this way is an H-gain graphic matroid. Okay, so it depends upon the labeling from the group H.
So
Yep.
in the third line,
Mhm.
definition, like the cycle can be both like either balanced or
No, if I want the set to be independent, I cannot contain any balance cycle.
right.
Okay, so at no balance cycle at all, and at most one cycle per connected component. So if I have a cycle and I want the set to be independent, it must be unbalanced. It must have a non-identity product around that cycle. Okay, any other questions? All right, so now we have the class of H-gain graphic matroids. I'm not going to spend a lot of time motivating our reasons for caring about H-gain graphic matroids, but I will say something. I'll say something fairly vague. Representable matroid. So a matroid is an abstraction of the idea of finitely many points arranged in space. I haven't really motivated that idea, so you'll just have to take my word for it. We can think of matroids in a geometrical way. They are abstractions of finite geometrical configurations. What are you doing when you represent a matroid with vectors? What you are really doing is you are applying coordinates to the points in that geometrical configuration. So a representable matroid is a coordinatizable matroid. Every set of coordinates is a vector, so it's a sequence of numbers from a field. What are we doing when we represent a matroid with a game graph? We are really we are giving coordinates to those points in the geometrical configuration using a group. So in both cases, it is though we are giving coordinates to points in the geometrical configuration, but we are using different algebraic objects. We're using either a field or a group. Okay? Now these two classes are really fundamentally important. There are various theorems that I could point to support that assertion, but I won't really explain those theorems. I'll just say that because of the structural work in big matroid structure projects by Jim Gielen and Bert Harrads and Jeff Whittle, I'll talk more about them later, because of the kind of structural work they are doing, which mirrors the kind of structural work by Robertson and Seymour on the graph miners project, because of the structural work, it is now clear that if we want to understand the structure of classes of matroids, we really need to understand representable matroids, and we really need to understand game graphic matroids. They are somehow symmetric and orthogonal to each other. Both types of classes play fundamental roles in the structure of matroid theory, if you want to understand the structure of classes of matroids. Okay, so one of the things I'll be trying to do for the remainder of the talk is find analogues for game graphic classes of results that already exist in representable classes. Representable classes have been studied throughout the entire history of matroid theory. Game graphic classes have received less attention, but we have reason to believe that the two classes are just as important as each other, and we should really treat them with equal respect. So that's really what I'm trying to do. I'm trying to give some additional respect to game graphic classes. All right, that's enough sort of motivation. I won't really give much more motivation for why we should care about these game graphic classes. Instead, I will move on to the main topic of this talk, which is monadic definability. Okay, so monadic second-order logic is a type of formal logic that you often encounter in discrete mathematics. It's actually really more like a family of logics. You have a different flavor of monadic second-order logic depending on what type of structure you're talking about. So you'll have one language for matroids, another for graphs, another for whatever discrete object you're thinking about. So what does it look like for matroids, monadic second-order logic for matroids? So you'll have variables which represent elements of your ground set. You will have variables which represent subsets of your ground set. You want to be able to talk about the relationships between those variables. So you want to say when they are representing equal elements or subsets. You want to be able to say when one element is contained in a subset. You want to be able to say when one subset is contained in another. So that takes care of the top three lines here. You also need to be able to say something matroidal. So we'll have an independence predicate. So we'll think of that as being a function which takes as input a variable. That variable represents a subset, and this predicate will return a truth value. It says true if it's independent in the matroid, and otherwise it says false. Okay? And then we have standard ingredients from any logical language, so standard logical connectives, such as the conjunction, disjunction, or negation, not, implication, if-then statements, equivalence, as well as the standard logical quantifiers. So the existential quantifier and the universal quantifier. And MSO, monadic second order logic, is just a collection of formulas that we construct from these ingredients. So let's do an exercise. Sorry, go ahead. Yeah.
Why 0 in the lower, the subscript?
Yeah, so this is a convention started by Peter Lenny. Now, why did he choose 0? Oh, it's by contrast with monadic second-order logic for graphs, I think, right? So for graphs, you have MS1 and you have MS2. And Peter, I assume this is what Peter did. Okay, well, it's not graphs, so it's not MS1, it's not MS2, so it can be MS0.
They allow predicate with unbounded.
Yeah, exactly. Yep. Okay, let's do an exercise to get our intuition for this language. So what is this sentence actually saying? So, well, let's try reading it out. For every set x1, if x1 is not independent, so if x1 is dependent, then something, then what happens? there exists an x2 with the property that x2 is contained in x1, and furthermore, for every set x3, if x2 is in x3 and x3 is independent, then x2 is equal to x3. Oh, actually, I think I'm missing something here. I want to say that x2 is independent. Okay, so just imagine that I've said that x2 is independent. Okay, so if x2 is independent, then what is the last line saying? Assume that x2 is independent, then this string of symbols is saying what? It's maximal independent, right? Okay, so what's the name of a maximal independent set? Basis, okay. So it's saying, so it is saying that x2 is a basis, right? Assuming that x2 is independent, the bit that I've left out, then this last line is saying that x2 is a basis. Okay, so let's go back. What is the sentence actually saying? For every x1, if x1 is not independent, then it contains a basis. So every dependent set contains a basis. That's what this is saying, right? Okay, so some people here will know what class of matroids that characterizes. What type of matroid is characterized by the fact that every dependent set contains a basis? Uniform, right? Yeah. This is the class of uniform matroids. Okay, so with that MSO sentence, we have just characterized the class of uniform matroids. So I would say that the class of uniform matroids is MSO definable. That's exactly what it means to be MSO definable. There exists some sentence in this language which is satisfied by exactly the matroids in that class. Whenever I have a class of matroids, that's what it means to be MSO definable. There exists some sentence which is satisfied by exactly the matroids in the class. Okay, any questions so far? Okay, so why do we care about this particular logical language and not other logical languages? It's because of its connections to complexity theory and the theory of computation. That's exemplified by Courcelle's theorem, which is actually a theorem for graphs, really hypergraphs, but there are matroidal analogues of Courcelle's theorem. So Courcelle's theorem is saying, take a class of graphs, if it's monadically definable, then I can recognize the graphs in that class in polynomial time. So there is an efficient algorithm for recognizing graphs with that property, assuming that I restrict my input to graphs with bounded tree width. I won't say more about what tree width is, but it bounds the structural complexity. So this is surprising because there are monadic properties like Hamiltonicity and three-colorability. Those properties can be defined monadically, but we can't recognize Hamiltonicity and three-colorability in polynomial time, right? Not unless the world collapses. Not unless P is equal to NP and everybody's got bigger things to think about. So Courcelle's theorem is saying that hard properties to recognize become easy to recognize if you restrict your input class by bounding its structural complexity. So that's what makes this an interesting theorem. It's right in the intersection of three areas of mathematics. It's talking about the structure of discrete objects. That's what the tree width is doing. It's talking about complexity theory, the theory of computation. That's what the polynomial-time algorithm is doing. And it's talking about the expressive power of logical languages. So this theorem is right in the center of that Venn diagram, those three circles. And I think the intersection of those three circles contains a lot of really beautiful mathematics, and Courcelle's theorem exemplifies it. So that's why we care about this particular logical language, because of its connections to the theory of computation. Okay, so now presumably we're sufficiently motivated to ask the question, when is a class of matroids MSO definable? Which classes of matroids can be defined in this way? Which natural classes of matroids are MSO definable? So I'll need a little more background here. I need to talk about matroid minors. I won't go through the definitions. I'll just talk about by analogy with graphs. So if you know graph minors, then you know that we can take a graph and look at an edge in it, and there are two ways of removing that edge. We can either delete it, which means erasing it, or you can contract it, which means identifying the edges and then erasing it. Identifying the end vertices and then erasing it. So I'll just say that there are matroid analogues of these operations. And just as in the graph case, if I start from a matroid and then perform a sequence of deletions and contractions, the result is a minor of the matroid that I start with. Okay, so that's all matroid minors are. They're just analogs of graph minors. Okay, if I have a class of matroids, and whenever I pick a matroid in the class and perform deletions and contractions, I get another matroid in the class, then that class is minor closed. This is exactly analogous with a minor closed class of graphs. If I have a minor closed class of graphs, then I can talk about the excluded minors. So the excluded minors are the matroids that are not in the class, but if I remove any element by deleting or contracting it, then I get a matroid that is in the class, right? So they are things that are just outside the class. The most famous example of an excluded minor characterization would be what? Any opinions? The most famous excluded minor characterization in history? Oh, okay. You're thinking of a matroid characterization, and I think you're absolutely right. Within the world of matroids, yes, the binary matroids is probably the most famous excluded minor characterization. Within the world of graphs, Kuratowski-Wagner theorem, right? So a graph is planar if and only if it doesn't have K5 or K33 as an excluded minor. So if you know that theorem, then you've got the right motivation. Okay, so the excluded minors characterize a class because a matroid belongs to the class if and only if it doesn't contain any of the excluded minors as a minor. Now here's an observation. Okay, let's talk about Rotter's conjecture. Unlike the case with graphs, a minor closed class of matroids may have infinitely many excluded minors. That happens all the time. But Rotter conjectured that in some famous cases, you will have only finitely many excluded minors. If F is a finite field, and you consider the class of matroids that can be given coordinates from F, that's a minor closed class of matroids, and it will have only finitely many excluded minors. That's a conjecture that Rotter made 50 years ago, more than 50 years ago. And now Jim Gielen, Bert Gerards, and Jeff Whittle have announced a proof.
No.
11 years ago.
Yes, yeah, well, it's a long proof. Yeah, work continues. Yeah, that will be written up and published, and nobody's looking forward to refereeing it. It's going to be a lot of hard work. Okay, now this gives us monadic definability for some classes because of an observation by Peter-Lenny, originally made by Peter-Lenny. If I have a minor closed class of matroids and it has finitely many excluded minors, then it is monadically definable. Okay? So, Rotter's conjecture now tells us whenever F is a finite field, then the class of F representable matroids is monadically definable because it has finitely many excluded minors. Right, but how do I prove that a class is not definable? It's not enough to say that the class has infinitely many excluded minors, because I can exhibit a minor closed class which has infinitely many excluded minors, but it is still monadically definable. That is possible. So how do I go about proving that that a particular class is monadically non-definable? Okay, well, there's a technique, and I can explain that technique by going to an older theorem, the Mayhew-Nerode theorem. So this is a theorem about the monadic second-order logic of strings. So I want to think of a string. A string is just a sequence of symbols, right? And the symbols come from a finite alphabet. So sigma is my finite alphabet. It's actually helpful if I think about a string as being a function. It's a function going from a set of positions into the alphabet. And the set of positions is just a linearly ordered set. So take an initial segment of the positive integers. Okay, so the string A, B, A is actually the function which takes 1 to A, 2 to B, 3 to A, 4 to A. Okay? Any set of strings is a language of strings. And I have a monadic second order logic for strings. Now this is going to be very similar to monadic second order logic for matroids. My variables represent positions, or they represent sets of positions. And I need to be able to talk about something string-like. So I do that by having a predicate for every symbol of the alphabet. So if sigma is a symbol in my alphabet, then this predicate will take as input a position variable and it will return a true or a false. It will return true if the symbol in that position is sigma. Okay? And the only other difference is that I'll have a binary successive predicate. So that says this position follows immediately after this position. So let's do another exercise. This sentence here in the monadic second order logic for strings, what is this characterizing? I'm imagining that I've got an alphabet of two symbols, A and B. So what strings are characterized by that sentence there?
Is that a string either, so whenever you have A, then next one is B?
Whenever you have A, the next one is B, right?
Yeah.
Yep.
The one before is B, right?
No, I mean.
It depends on how you interpret it. Yeah. I'm going to say this means P1 is the successor of P2. Yeah, it would be entirely reasonable to interpret it the other way about it, sure. Yeah, so if we interpret successor in that way, this is saying whenever P1 follows immediately after P2 and there's an A in P2, there has to be a B in P1. So what's that characterizing? It's just characterizing the strings where you have no AA, right? You can have everything else, but you can't have a double A in the string. Okay, now what languages are monadically definable? So Mayhew gives us an answer to that question. Now, curly L is a language of strings. I'm going to define an equivalence relation relative to curly L. So W1 and W2 are strings, and I say that they are equivalent if they are both in curly L or neither one is in curly L. And furthermore, that relation holds no matter what I append to the end of W1 and W2. Okay, so I take any string I like, call it Z, I append it to W1 and W2, and the resulting strings are both in curly L or neither one is in curly L. This is an equivalence relation. Mayhew says that the language is definable in monadic second order logic if and only if this equivalence relation has finite index, so it has finitely many equivalence classes. So this gives us a tool for proving non-definability. All right, let's apply it. Let's apply it to the language of palindromes. Okay, palindromes just means same backwards as it does forward. So there's a mirror image. If I mirror the string down the center, I get the same string. All right, so I have an infinite matrix here. The rows and the columns are labeled by strings, and in every cell of this array, I've put either a tick or a cross, which says whether or not that concatenation is a palindrome. All right? So if I concatenate AB with BA, then I get this palindrome. I get a Eurovision winning palindrome. But if I concatenate AB with BAA, then I don't get a palindrome, so I put a cross there. Okay so far? Right, now what does this mean? What would it, if I had two strings labeling rows and they were in the same equivalence class, what would it tell me about those rows? Anyone?
They would have the identical.
They'd have to be identical rows, wouldn't they? Yeah, because no matter what I append to them, they are either both palindromes or neither palindromes. So I would get two ticks in that column or two crosses in that column. So if two rows are in the same equivalence class, those rows look identical. What do I see in this matrix? I see no two identical rows. So no two strings labeling rows are in the same equivalence class. That means that I've constructed infinitely many equivalence classes. Therefore, Mayhew tells me the language of palindromes is not monadically definable. It's pretty clean, right? This is a nice proof. Okay, now we can use the same philosophy for matroids. So I'm going to have to figure out what it means to concatenate matroids. If you're familiar with matroids, then you'll be familiar with operations which glue matroids together, like direct sum and generalized parallel connection and things like that. Actually, our lemma doesn't really require a particular gluing operation. It just needs to be something reasonable, some reasonable operation for gluing together matroids, where I won't say what reasonable means, but I will kind of say what reasonable means. it just means that there shouldn't be too much information flowing across the partition in the gluing together. And I won't really say what that means to have information flowing across that partition. But any reasonable way of gluing matroids together is going to work for this lemma. So I make the same definition of an equivalence class. Curly M is a class of matroids. I'm going to define an equivalence relation relative to M1 and M2. I take M1 and M2 are matroids. I say that they are equivalent if they are both in curly M or neither is in curly M. And furthermore, that relation holds no matter what matroid I glue to them. So I take any matroid N, I glue it to both M1 and M2. The resulting matroid, they should both be in the class curly M or neither one should be in curly M. In that case, I say that M1 and M2 are equivalent. And our lemma says, if the class of matroids is monadically definable, then there are only finitely many equivalence classes under this relation. So this is our analog for Mayhew-Royd. Any questions about that lemma?
Can you prove it from the string version, or do you have to redo everything?
It's easier not to. I wouldn't recommend it. I'm going to say no. I don't think you should try and prove it from the string version. I think it's just easier to. Yeah, I don't see any easy way to do it. Just using that string version as a tool.
But this depends on the definition of this gluing operations, right?
Well, actually, no. You can prove this lemma in a way that is independent of the gluing operation. You have certain constraints on what gluing means. But it's pretty generic.
Right?
It depends on reasonability. Yeah, exactly. And actually, you can generalize it further so that it's not a lemma about matroids, it's just a lemma about hypergraphs. And then when you're talking about hypergraphs, you can actually throw out the idea of gluing together. You just sort of need to say that there exists a reasonable partition. So it's not really like you've glued, it's a little bit as though you've glued two hypergraphs together in a reasonable way. So this is actually not a matroidal lemma, it's a hypergraphic lemma.
And by gluing, you mean some kind of thing that can be described by monadic second order logic formula?
It's not that the gluing operation needs to be definable in monadic second order logic, it's that the sets on one side of the gluing operation the sets on this side of the gluing operation should not look like they belong to too many different equivalence classes from the perspective of the sets on this side. Where maybe we can talk afterwards. Yeah, if I go into the weeds here, I won't finish. But anyway, in any case, you can extend this to hypergraphs, and there is no particular gluing operation that you require. Okay, but we applied this to game graphs, right? So we started from an infinite field. F is an infinite field, and we constructed a sequence of game graphs labeled with elements from the multiplicative group of that field. So alpha is an element from the multiplicative group, and I just want alpha to have high enough order. I'm able to do that because in an infinite field I can find elements of arbitrarily big infinite order, so I'll just choose a different alpha for each game graph if necessary. I'll just choose an alpha which has high enough order. These game graphic matroids label the rows of my infinite array. There are other game graphic matroids that I use to label the columns of my infinite array, and I fill in the entries of the array with a tick or a cross depending on whether the gluing together is F representable. I find exactly the same infinite array. I've got ticks down the diagonal, I've got crosses everywhere else, so I can use exactly the same argument before to conclude this theorem. If F is an infinite field, then the class of F representable matroids is not monadically definable. Okay. So now we have a nice dichotomy. F is a field, the class of F representable matroids is monadically definable if and only if F is finite. That's quite beautiful, nice and clean division. I've been saying that I want to give analogues for game graphic classes of theorems that exist for representable classes, so let's ask the same question for game graphic. For which groups H is the class of H game graphic matroids MSO definable? Okay, so that's our motivating question. So here's what we can get immediately from the work we already have. That proof that I just gave you with the game graphic classes using elements of arbitrarily high order, well, if I have a group H with elements of arbitrarily high order, then I will go through exactly the same argument, and I will conclude that the class of H game graphic matroids is not monadically definable. Okay, so that's a big class of infinite groups taken care of. So in this Venn diagram, so this is a Venn diagram that you've seen before if you were at my talk a week ago, but I'll explain it in a little more detail. The universe of this Venn diagram is the universe of infinite groups. And I have drawn an ellipse around the groups which do not contain elements of arbitrarily high order. So inside the ellipse, you have some upper bound on the order of every element. Some upper bound which bounds the order of any element at all. Okay, in the language of group theory, such a group has finite exponent. Okay, so I've coloured red all the groups which do not have finite exponent because red stands for non-definability. Any group in the red area, I know that I have a non-definable class of game graphic matroids. Inside the ellipse, well, the easiest example is something like an infinite direct product of a finite group. Take infinitely many copies of a finite group and just take the direct product of all of those things. That certainly has finite exponent, so it's inside the group. You get more sophisticated groups like the Tarski monster. I won't explain what that is. Here's another ellipse which we proved with a different application of the Mayhew-Matroid theorem. So inside this ellipse, you have all the groups where a finitely generated subgroup is itself finite. In the language of group theory, such a group is locally finite. So locally finite means finitely generated subgroups must be finite. If you fall outside this ellipse, then if H falls outside this ellipse, then the class of H game graphic matroids is not monadically definable. Okay, we can prove that with a different application of Mayhew-Matroid. Okay, so that takes care of the Tarski monster. The Tarski monster had finite exponent, but it is not locally finite because it has, in fact, the Tarski monster is an infinite group generated by only two elements. Over here we have rationals modulo integers. This is locally finite, but it just does not have finite exponent. Okay, but we still have this white space in the middle where I haven't said anything about definability or non-definability. And there's a reason for that, because actually there are some groups in that white area where the class of game graphic matroids is monadically definable. So I'll work up towards that now. Okay, so this is work in progress with myself and Daryl Funk. This is a consequence of what I called last week the representation theorem. It gives us some control over the different ways in which game graphs can represent game graphic matroids. Different game graphs can represent the same matroid. I want to have some type of control over that, and our representation theorem will give us some control. And as a consequence, we're going to be able to add a predicate to our monadic language. And this predicate will be true for vertex stars of the underlying graph for some representation. So if the matroid has a game graphic representation, then I will have an extra predicate which is now true for the sets which are vertex stars. When I say vertex star, I just mean the set of edges instance with a vertex. Okay? Now, once I have augmented my language with that predicate, the language gets much more powerful because I'm able to say things like, this set of edges forms a connected subgraph. I'm able to talk about there is a path from this vertex to that vertex. I'm able to use this to talk about vertices. I can talk about connectivity of a subgraph. I can talk about a subgraph being a cycle. Okay, so this gives me a tool for defining the class of H game graphic matroids when H is a finite group. So here's how I do it, roughly speaking.
I have a question.
Yeah,
So
go ahead.
When you say about a star, that's under some representation,
Yes.
right? So you might have
Yes.
two distinct representations.
Right.
And then the formula will say this set is vertex star, that set is vertex star, even though you
Right.
might not have a representation realizing them at the same time.
So I get away with this by using non-determinism. So I'm going to use the existential quantifier to pin me down to a particular representation. So I'll say there exists sets x1, x2, x2, x3, up to blah, 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 such that relative to that choice of those sets, this predicate picks the vertex stars for a representation. If I'd used the existential quantifiers to choose different sets, I would have ended up with a different representation. So it's a perfectly, it's a good observation. I am not saying that there is a unique representation or anything like that. I'm saying that I'm using non-determinism to pick out a particular representation. Okay. Does that resolve that question? Yeah.
So, okay, so can I interpret as like, so you're defining this vertex star unary predicate,
Yep.
not from the usual relation for matroids, but using MSO transduction.
It's an MSO transduction.
Right.
So in the language of transductions, it is a transduction from the matroid to all of its gain graphic representations.
Right. I see. And this particular unary predicate, does it say that, is it unary predicate?
It is a unary predicate, yeah.
So what does it query? What can you query exactly using the predicate?
Some set of edges is a star, right?
Yeah, but you said it's a unary predicate.
So it's MS1. It's a transduction from the matroids to the MS1 language of the graphical representation. I'm allowed to talk about, to the first order language of the graphical representation. I'm allowed to quantify only over vertices of the graphical representation. The unary predicate stands for the vertices. So I can quantify over vertices by quantifying over sets, which are vertex stars.
Set meaning?
A set of the matroid.
Set of edges?
A set of the matroid, which is a set of the edges, yeah.
Right.
So I'm allowed to quantify only over vertex stars, which is really the same as quantifying only over vertices. So I basically give myself access to the first order language of the underlying graph.
Right. But anyway, the predicate is in the form of like whether this set of edges, like set of elements of the matroid is forms of vertex star.
Exactly. Yeah. Okay, so with access to a logical language for the graph, I can now say when there is an H-gain graphic representation. I'll go through this briefly. What I do is I partition the edge set into blocks where every block corresponds to an element of the group H. This is where I'm using the finiteness of the group H. Okay? So every edge of the underlying graph has now been labeled with an element of H. I've used the existential quantifiers to correctly guess a labeling of the group. Now I want to know whether the cycles that are dependent in the matroid have the proper product as I walk around them. And I do that. I think this trick is in your thesis. I don't know whether it was your idea or somebody else's idea. I've been meaning to ask you about this for several years. This is apposite. So the trick is, I first of all apply the labeling using elements of the group, and then I want to check the product as I walk around a cycle. So I apply a new labeling, which means partitioning up the edges, which corresponds to the partial product as I walk around. So I have essentially applied a new labeling which keeps track of the partial product as I walk further and further around the cycle. I add extra structure to my sentence to enforce that the labelings of the partial products are correct. So every partial product of this edge I obtain by taking the partial product from the previous edge with the label on this edge. So I can enforce that with extra clauses in my monadic sentence. And then I can say, what is the product around this cycle? I can say this is the identity. Okay, so I'm not sure where that idea comes from originally. I think I saw it in your thesis, but...
Stefan Kreutzer
okay.
taught me that.
Okay, great. So great. Maybe it's original with Stefan. Anyway, it's certainly not original with me or Daryl or any of my co-authors. Okay, so but doing that, I can check whether this matroid has an H-gain graphic representation when H is a finite group. And all I'll do is I will note the structure of that sentence. The sentence is basically saying there exists some partition of the edges such that for every cycle blah 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 holds. That's the essential structure of the sentence. Now, this works for some infinite groups. By getting another alternation of quantifiers, I can make this strategy work for some infinite groups. So, in particular, say that I take infinitely many copies of the group of size 2, and I take the infinite product of that group. Then I can get a similar type of a sentence characterizing the H-gain graphic matroids when H is that infinite group. I won't go through the details in this, but I will just point to the structure of the sentence. It says, for every independent cycle, there must exist a partition such that for every dependent cycle. So I've introduced another alternation. And I can actually take that a step further. I'll introduce another alternation of quantifiers, and this will correspond to a group semi-direct product. So I'm going to take my infinite direct product of a finite group, and I'm going to apply a semi-direct product to that. So now, here's my infinite product of a finite group. I'm going to apply a particular semi-direct product with a finite group. Call H the result of that. The class of H-gain graphic matroids is again monadically definable, and the sentence will look like this. There exists a partition such that for every independent cycle there exists a partition such that for every dependent cycle. So at this stage you might suspect that we can keep on doing this alternation, and in fact we can. So the alternation of quantifiers in the sentences corresponds to alternations between infinite direct products and semi-direct products. So we get an infinite hierarchy of groups. You start with a finite group, take an infinite direct product, then take a semi-direct product with a finite group, then take an infinite direct product, then take a semi-direct product with a finite group, and so on and so forth. Any group H which you obtain in this way gives rise to a monadically definable class of H-gain graphic matroids. Okay, so I haven't really said much about the structure of these groups, but I hope it's okay. I've got this hierarchy of infinite groups. Any one of these groups gives rise to a definable class of H-gain graphic matroids. This is work that I did with Sapir Ben-Shahar last year as part of our senior year project. Okay, so what does our Venn diagram look like? We have a blob of blue in the middle. So the blue corresponds to infinite groups H, where the class of H-gain graphic matroids is definable. I think this picture is much more interesting than if the picture had just been all red, as it was with the case for fields, right? So for fields, we had a very clean answer. For groups, we have potentially a kind of messy answer, but the world is much more interesting. So where is the boundary between red and blue? Still don't know, still don't really have a conjecture, but I think it might be close to that blue circle that I've already described. So the reason I think that might be the case is because of a conversation that I had with Angus Matthews. Angus is a first-year PhD student in Leeds. I gave a talk about this material back in February, and Angus got very interested in it. In particular, he got interested in this lemma. Now, I'm not going to talk about this slide because I want to get to the end. But basically, the point of this lemma here is that saying that if H is an infinite group and a particular auxiliary graph, which I've defined in this slide, has a particular structure, then the class of H-gain graphic matroids is not monadically definable, right? So the contents of the slide, which I'm not going to talk about, it's providing tools for somebody who really knows group theory to prove that the class of H-gain graphic matroids is not monadically definable. Now, I don't know a whole lot of group theory. I mean, I've been talking to group theorists, but there's a lot of group theory to learn, and there's plenty that I don't know. Angus does know quite a lot of group theory, and he knew exactly where to look in the group theory literature to find a construction which he was able to modify. And so what Angus did was put in one extra red dot in my Venn diagram. Actually, the theorem as I've stated up here is not quite correct, because the existential statement that there must be red in this white area, that's obviously true just by counting arguments. Right? There are only countably many blue groups, right? Because there are only countably many sentences in monadic logic. There are uncountably many infinite groups. Only countably many blue. There are uncountably many groups in this intersection. Only countably many can be blue. So just by counting, I know that there are just red dots. What Angus did was actually more interesting than that. He exhibited a particular concrete specified group, which is coloured red. So the statement up here is not actually what Angus did. His real theorem would be, construct a group in this way, then it does have finite exponent and it is locally finite, and yet the class of H-gain graphic matroids is non-definable. So that's really what he did. He took a specific group in this area and coloured it red. Anyway, it's been fun talking to Angus about this problem. And he has some model theoretical intuition that this blue area that I've already coloured in might be close to the correct boundary. So we might actually find the true boundary between definability and non-definability in this Venn diagram. It remains a hard problem, but I'm more optimistic than I was a year ago. Okay, I think I've got to stop there. Thank you.
Thank you. Any questions? Is there any chance to extend the language, give more powers by allowing extra predicates so that we can do more?
So what sort of predicates would you like to add?
Well, something related to group or...
Yeah, I mean, look, you're in charge, right? You can do whatever you like. The reason for not doing so is that you might lose the connection with theory of computation. So Courcelle's theorem will break if you add too much power to your language. You need your predicates to be decidable by a tree automaton, really. That's how Courcelle's theorem is proved. So there are certain things, if you add too much, then you'll lose that connection. So that's why I kind of liked staying in the fairly restricted world of monadic logic. Yep.
So, I mean, for fields, do you really need Rota's conjecture to get
Good question. Well, this is what Sangil was asking last week, right? And actually, Anjan, maybe so you've been thinking about transductions from a matroid to a representation of that matroid.
Yeah, but that was for like really particular
Yeah.
case.
So whether it can be done in the general case seems a little bit unlikely to me, but... so you'd be looking for a transduction from a matroid to a vector representation of that matroid. A bit hard to imagine how it can be done. So for now, we are required to use Rota's conjecture. Yeah. Don, you had a question?
So among these your blue part, is there any H which has infinitely many excluded minors?
Every infinite group H, if H is an infinite group, the class of H-gain graphic matroids has infinitely many excluded minors. So every group in this Venn diagram. That is a result which is in Darrell Funk's thesis. So so the groups in here, that class has infinitely many excluded minors, but it is still monadically definable. Yep.
Just to clarify, so usual definability doesn't rely on this like random like coloring, right? But you're using backward translation lemma like inside the bracket, I guess.
I'm not sure I follow. So
yeah, so I'm slightly confused about like what we mean by definability.
Oh,
yeah.
I understand.
Yeah,
right.
yeah,
so
yeah.
Right, the colouring and the copying operations
So,
within the transduction.
Yeah.
I have not yet found a matroid application where I need copying and colouring in the transduction.
Yeah, I mean, but in your so in your definition, MSO definition of H-gain graphing matroid
Yeah.
with finite group.
Yeah.
You use the coloring, right? So
Yeah,
you're
yes,
creating this,
the non-determinism.
Yeah,
right, so
yeah,
I'm
yeah,
using
yeah.
colouring there.
Yeah,
Yeah,
you're using
sure.
coloring there.
Yeah.
So I'm now confused, like in the usual, like a traditional classic definition of definability. For example,
Right.
in the Mayoral theorem.
Yeah.
So do we allow coloring? So I think you can easily circumvent this issue by using backward translation lemma. This is more about like technical question.
Yeah, so I have. Yeah, I think I'm just saying I'm using non-determinism to guess an underlying graph, and then I'm using non-determinism to guess a group labeling of the edges, and then I'm just checking that every cycle has the correct product. Or rather, I'm checking that every cycle that should have the identity product does have the identity product, and every cycle which shouldn't have the identity product doesn't.
Yeah.
So, I mean, that is using non-determinism, but I don't think it's using backward translation, is it?
Yeah. So because it depends on like what we mean,
What I
mean
mean.
by definability.
Right.
So you are given this relational structure with a fixed
Yeah.
vocabulary,
Yeah.
and in
Yeah.
the vocabulary you don't have this star vertex star
Right.
predicate.
Right. Yeah.
And then maybe you will ask.
Yes.
the-
Okay. I see what you're saying. Yeah. I guess that is an implicit use of backwards translation.
Right.
Yeah. Yeah. That's right. Yeah. Because I'm going backwards to the relational structure which doesn't have the vertex star predicate. Yeah. Sure. Sure. And I'm using lots of non-determinism, so I'm using lots of colouring.
Any other questions? If not, let's think the